Hello guys, this is Edward. Welcome to another lecture on mass spectrometer. Previously, we had discussed how to identify fragments that makes up peaks in mass spectrum, and that is basically A-level curriculum. So today we are going to look at how to analyze mass spectrum itself, how to analyze mass spectrum and identify the compound that it belongs to, and it's more advanced than A level. It is for undergraduate and postgraduate level. Okay, so to get started, there are a couple of things you need to know um, why analyzing or before you be able to analyze mass spectrum. And they are molecular ion, that is the M plus. Okay, so this basically corresponds to analyte or that has not been fragmented. Okay, the analyte molecule that has not undergone fragmentation, that is the molecular ion, and it's usually located at the extreme end of the spectrum. So let's say you have a spectrum like here. So the last peak is usually the M plus. Okay, so that is it. And another thing you need to take note of is the isotopes. And these are the things that you need to know before you be able to analyze mass spectrum. So isotopes in mass spectrum, you should always look out for isotopes like chlorine, bromine, you have carbon, you have silicon, yeah, sulfur, okay, and iodine as well. Okay, so they usually leave an interesting pattern in the spectrum. For example, chlorine. Okay, so if you see a spectrum that contains chlorine molecules, you will see an interesting pattern of isotopes. Let's say, of course, we know that chlorine has two isotopes, 35 and 37, right? And they are in ratio, the relative abundance are in ratio of 3 to 1. Chlorine 35 is more abundant than chlorine 37, right? So if you see um, a compound that contains chlorine, you will see two isotopes, two peaks, see basically interesting peaks like this. Okay, and that's for isotopes. There is something else we call nitrogen rule. You need to know this nitrogen rule. Nitrogen rule. No, it's very interesting because it helps us to know or to determine if there is nitrogen present in that molecule. If the M plus is odd, it shows that there is possibility of a single nitrogen being present in that molecule. Okay, and if the M plus is even, there's a possibility of the there's a possibility of two nitrogen present in the molecule or zero nitrogen present. Okay, so that is what nitrogen rule is all about. It's going to help you to identify, to know if there's a nitrogen present in the compound. Okay, so now another thing also you need to look at, you need to know is most of these functional groups have a signature peaks, okay, at which you use to identify them. Okay, now aromatic compound, okay, or let's say the aromatic compounds or aromatic rings, they usually have what they call a prominent molecular ion. Okay, they're a prominent molecular ion, which means that molecular ion is very like it's large or big. Okay, they have big molecular ion. Maybe it could be as tall as this. If this is M plus, if this an aromatic compound, okay, they have a prominent molecular ion, M plus ion. Okay, and they also usually have a common peak at M minus 1. Okay, now this is M plus 1, right? So usually they'll have prominent peak at M minus 1, like a here is M minus 1, Okay, here is m plus 1. Okay, so they usually have a prominent peak at m minus 1. Okay, so that gives us that is like a giveaway to know that this compound probably might be an aromatic compound. Also, they usually have a peak at 77. Peak at 77. That is because of what? Of the benzene, right? Benzene. Okay, so they usually have peaks at 77. Now that's for aromatic um, compounds. Okay, now also let's look at alcohols. Okay, now alcohols usually have small molecular ion. Their M plus is usually small. Okay, and sometimes they are undetected. Okay, if the alcohols are tertiary alcohol, and they usually show a prominent peak at 31. They usually show a prominent peak at 31. Okay, and that is due to the presence of the OH. Okay, so then and also another thing to know here is that in primary alcohols, their peak at 31 are usually very prominent. Basically, they are the base peak. Okay, but if it's secondary alcohol, okay, the peak at 31 might not be that prominent. Okay, so for primary alcohol, the peak at 31 are larger, okay, are more prominent than secondary alcohol. Okay, and also in secondary alcohol is more prominent than tertiary alcohol. Okay, I'm talking about the peak at 31. Right, so that's for alcohol. Let's look at another functional group, amines. Okay, so now nitrogen in amine can be detected by its odd molecular weight. Okay, by its odd M plus. Remember we said that in nitrogen rows, if the M plus is odd, it means there's a possibility that it contains nitrogen, right? All right, so now mostly the straight chains amine, okay, their molecular ion are usually not detected. The molecular ion of straight chain amines are usually not detected. Okay, they are usually not detected. All right. Now the base peak in most amines are usually around MZ at 30. Okay, so when you see peaks at 30, that is a giveaway that the compound is amine, and couple the fact that it has odd molecular weight, or odd M plus. Okay, it's also another giveaway to show that it contains amine, okay, or amines. All right, and don't forget also their molecular weight. The M plus peak is usually not it's not prominent. Okay, it's not prominent. Sometimes can be not detected. It cannot be detected if it's a straight chain amines. All right, so let's look at another functional group, and let's look at ketones and aldehydes. Ketones and aldehydes. Okay, now ketones, these functional groups, they usually have very prominent M plus molecular ion. Okay, they usually have a prominent molecular ion peaks. Okay, prominent, and most especially in ketones. Okay, and they usually have a base peak or peak at 58 and 86. Okay, but mostly peak at 58 is a giveaway to show that the compound is either ketones or aldehyde. Okay, so prominent M plus and peaks at 58 and 86, but mostly peaks at 58. Okay, so that's for ketones and aldehyde. Let's look at another one. So let's look at carboxylic acid. Carboxylic acid. Carboxylic acid. Okay, so they usually have weak molecular ion. The M plus are usually weak if they are straight chain. Okay, they have a weak M plus, and they have prominent peak at 60. At 60. Okay, at M0 ratio of 60, they have a prominent peak. That's a giveaway to show that that compound um, is contain carboxylic acid. Okay, so let's look at this question. We are to interpret the mass spectrum below and deduce the structure or the molecular structure of the analyte. And while doing so, you have to include your mode of reasoning, or like how you're able to come into conclusion. All right, and the first thing to do is to write down the molecular ion, look for the molecular ion from the spectrum, and our molecular ion here is 101. Okay, so we write our M plus equals to 101. All right, the next thing to do is look for isotope. Do we have isotope here? Is there any interesting pattern? Okay, from the peaks here, no. So basically we have no isotopes, no. And then the next thing, let's look at the peaks here. Let's look at the fragment and identify the peaks there. You have a base peak. The tallest peak is the base peak at 30. Okay, so you write base peak 30. Okay, and you also have another peak at this fragment here, this cluster here. Okay, we have a peak. We have the tallest peak here is 44. Okay, you also have peak at 44. All right, now so the next thing is to look out for nitrogen rules. Do you have nitrogen in the compound? Nitrogen, I remember the nitrogen rule says if the molecular ion is odd, if you have an odd molecular ion, there is possibility that it contains nitrogen. Okay, and also to confirm that if it contains nitrogen, 30 is the characteristic peak for amines functional group. Okay, and amines contains nitrogen, right? So it means that this compound contains one nitrogen. Yes, okay, and it's one nitrogen. All right, now having done that, so now how do you know the compound, the molecular structure of the compound itself? So what I usually do is this is my own method. All right, there could be other method that works, but this is the method that works for me. Now I'll subtract the functional group. Okay, the value of the functional group the amines is represented using NH2, right? This is the functional group for amines, right? Now, what is the value of amines? Amines is 14 plus 2, 16, right? Now, what I'll do is I'll subtract 16 from the molecular ion. Okay, if I subtract it from molecular ion, I will have 101 minus 16. That will give me 85. So it means that 85 is the molecular mass of the carbon and hydrogen present, the alkanes present. Okay, that is the molecular mass of the alkanes present. So now to get estimate of the number of carbon atoms present, what I will do is I will divide the 85 by 12. Okay, I'll divide it by 12. Now 85 divided by 12 give us 7.08. Now, so basically what I'll then do is this: I'll estimate that the compound basically contain number carbon atom from 6 to 8. Okay, because you can't just work with 7. 7 might not work for you, right? So what I'll do is I'll estimate using I'll use estimate of 6 carbon atoms to 8 carbon atoms. So I will try 6, 7, and 8. Okay, whichever one that works that give me the value of what I'm looking for, right? So now let's assume you are working with carbon atom number 6. The alkanes that contain 6 carbon atoms is called hexane, right? Hexane, and hexane is C6H14, right? So let's find the value of C6H14. What is the molecular mass of molecular weight for this C6H14 of hexane? So 12 times 6 plus 14, and that will give us 86. Now remember, you have to substitute one hydrogen with amine, right? So if you minus 1 from 86, that will give us 85. Okay, so basically the compound contains 6 carbon atom, and which is hexane. Then if you now combine that with the functional group of amines, that will give us aminohexane or hexane amine. Hexane amine. Okay, so that is the analyte. Then let's draw the structure of hexane amine. So basically you're going to have CH3, CH2, 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 CH, then we can have our amine here, NH2, and then CH3. Okay, 1 2 3 4 5 6. So this is the molecular structure of our analyte. I hope that makes sense. So let's look at this question. We are to do the same thing, interpret the mass spectrum and deduce the molecular structure of the analyte. And while doing that, you also have to include your reasoning, how you come about, your conclusion. Okay, so the first thing to do is to look at the molecular ion, the M plus. All right, so our M plus is the last picked here, which is 74. Our M plus is 74, and also take note, our molecular ion peak is almost undetectable. Okay, so take note of that, so that will help us to identify the functional group that that is associated with that particular characteristics. Okay, all right, and next thing to check for isotopes. Do we have isotopes here? Do we have interesting pattern in the peaks? If there are isotopes that you see the patterns mostly especially on the molecular ion peaks. So from here we can see there is no interesting pattern here, and hence there is no isotopes. Okay, next thing is nitrogen. Let's use our nitrogen rule to see if the analyte contains nitrogen. If it contains nitrogen. Okay, and using the rule, it says if we have an even molecular ion, which is 74, right? Now it's either it contains 2 nitrogen or 0 nitrogen. Okay, now to confirm if it contains 2 nitrogen here, if it contains nitrogen at all, you should be expecting peak at 30. Now because peak at 30 is a characteristic peak for amines, and here we don't have any peak at 30. Okay, this is at 30, there is no peak at 30, so it means that there is no nitrogen present in the analyte. Okay, and now let us start identifying the clusters and the peaks. Okay, let's look at this cluster here. This cluster has a peak at this is 50, 55, 56. This cluster has peak at 56. So we write peaks. We have peaks at 56. Okay, and let's look at this cluster as well. This cluster here, the tallest peak on this cluster is 30. This is 35. This is 40, 41, what is 41, right? So we have peak at 41, and let's look at this cluster here. This cluster here, we have the tallest peak here at 31. Okay, and this cluster here we have 15. Now, which of these cluster here peak is, can you find interesting here? That is peak at 31 here. Okay, and which cluster, which a functional group is characterized with peak at 31? That is alcohols. And remember, alcohol also they have almost undetectable molecular ion. Okay, and you can see the molecular ion here is almost undetectable, and we have peak at 31. So this is a confirmation that this compound or this analyte is an alcohol. Right, and it's probably alcohol because the molecular ion at 31, this 31 here, sorry, the peak at 31, okay, it's abundant. It's abundant, okay. So if it is secondary alcohol, it won't be that abundant. It might be prominent, but not that as abundant as primary alcohol. Okay, so this is basically a primary alcohol. Now, how do we then know the compound, the molecular structure of the compound of the analyte? The same method we used previously. Now, alcohol has functional group of OH, right? And the value of OH is 16 plus 1 is 17. So we'll subtract 17 from the molecular ion of 74, and that will give us 74 minus 17. That will give us 57. That will give us 57. So 57 basically is the molecular mass of the alkanes, okay, that is present without the functional group of alcohol, without alcohol, right? So then I'll divide this 57 by 12. Divided by 12, that will give us the estimate value of carbon atom. Now it doesn't have to be exact, it might not be exact, okay? So we have 4.75. Now 4.75 doesn't mean that the carbon atom is 4. So what I'll do is this: I'll use a range of 3 to 5 carbon atom. So I'll work out alkanes that have 3 carbon atoms, okay, and check the value of what we'll get, and then compare that with 57. So now, which alkanes have 3 carbon atoms? We have propane. Propane is C3H8, and C3H8 will give us 12 times 3 plus 8, 44. Will give us 44. So 44 is not what we are looking for, and so it means propane is not the compound, it's not the alkane. And let's go for C4, 4 carbon atom, right? C4H 10. 4 times 12 plus 10, 58. Now we have 58. Okay, that is butane, right? 58. Now remember, we have to subtract one hydrogen, right? You have to substitute one hydrogen with the functional group. So 58 minus 1 will give us 57. So the compound contains 4 carbon atoms. And which alcohol contains 4 carbon atoms? That is butanol. Okay, butanol. So then let's draw the structure of butanol. The molecular structure of butanol, we have CH3, CH2, 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 then we have OH. Okay, I hope that makes sense. Alright, so let's look at the last question here. And before we continue, in case you haven't done so, kindly subscribe to my channel, like the videos, drop a comment if you have any question, and don't forget to turn on your notification bell so you get notified whenever a new video like this is dropped. Okay, so Now we have to do the same thing here. Interpret the mass spectrum, deduce the molecular structure, and while doing that, include your mode of reasoning. Okay, how you're able to come to the conclusion. I want you to pause the video and attempt the question. So let's do that together. The first thing to do is look at the molecular ion. Our M plus, our molecular ion M plus is 100. M plus is equal to 100. Let's look at, is there any isotopes here? Let's look out for isotopes. If there are isotopes, it will be visible on the molecular ion peaks here. So hence, there is no isotope. Let's look out for nitrogen. Let's use nitrogen rule. So our molecular ion is even, so which means it either contains two nitrogens or zero nitrogen. All right. So and if it contains nitrogen, you should be expecting peak at 30 for amines. Right? For amines. Sorry about that. Okay, you should be expecting peak at 30 for amines. But there is no peak at 30 here. There is no peak at 30. So there is no nitrogen present. Alright. Now so let's look at the clusters, the fragments, and then identify the peaks there. Okay. And this cluster here, we have peaks at, this is 85. Right. And on this cluster here, we have the tallest peak here at, this is 71, this is 85, this is 71. Okay, let's look at this cluster here. Here we have our tallest peak at, this is 55, 56, 57, at 57. And look at this cluster here. Here is where we have our base peak, and it's at 43. This is 43. And let's look at this cluster here. We have 20, 25, about 29. Yeah, this is 29. You have cluster, you have peak at 29. And if you look at here, there's a small peak here at 15. Peak at 15. Okay, so now let's look at this compound. Then let's look at the peaks. Do you have any interesting peak here that's you know, that give off a particular functional group? Okay, there is no peak at 30, so no amines. There is no peak at 31, no alcohols, and what else? There is no peak at 60, so there is no carboxylic acid. Okay, and there is no peak at 56, so there is no ketones or aldehyde. So basically, this compound, look at the, I want you to pay attention to the peaks here. Peaks at 15, this is what, this is methyl. This is methyl CH3 cation. 29, this is ethyl C2H5 cation. 43 is propyl C3H7 cation. 57, but so basically this compound is an alkane. Okay, this compound, this analyte is what is an alkane. This fragment are fragments of, you know, from alkanes, and the particular peak that is associated with alkanes is 43. You usually have a base peak at 43. because this is where you usually have what they call this is where you can have a possible rearrangement. That's where you have the most stable carbocation. Okay, and so that is the characteristic peak for alkanes. You have a base peak at 43. Okay, now I'm going to explain that later on. But so now we know that this compound is definitely an alkane. So how do we know the alkane it belongs to? This is the molecular ion is 100, right? 100. Which alkane has molecular ion of 100? To estimate, I divide by 12. Okay, 100 divided by 12, we have 8.3. But then I will start from 6 carbon atom to 8 carbon atom, right? So let's say 6 carbon atom is from C6 to C8. So from 6, 7 rather to C9. Okay, from C7 to C9. All right. So C7 is carbon number 7 on of alkanes is heptane, right? And heptane is C7H16. Okay, C7H16. What would that give us? 7 times 12 plus 16, and that is 100. So this spectrum is mass spectrum of heptane. Okay, I hope that makes sense. So now I'll be doing a part 2 video on this, and I will show you how I'm going to explain how, when fragmentation occurs, how you're able to get base peak of 43, how this base peak of 43 comes about. So sometimes you could be given questions like to sketch mass spectrum of analyte. Okay, so I'm going to explain that in my next video, the part 2 of this video. Okay, so I think that will be the end of today's video, of today's lesson. And don't forget to subscribe if you haven't done so, like the videos, and turn on your notification bell. See you some other time. Thank you.